Okay, so we'll now continue day 4 today. Good morning, students.
Good morning, sir.
Owing to the program yesterday, we're not able to complete day 4. So we're going to be completing day 4 today. We are going to continue from current electricity, which was where we stopped yesterday. Now, under current electricity, we're talking about voltage. And I remember telling you about how voltage is connected, right? Well, I don't think we've quite talked about resistance. Now, resistance is the opposition to the flow of current, right? And we said yesterday that a resistor is a passive component in the guy, right? And based on resistance, we classify conductors. We classify conductors as ohmic conductors and non-ohmic conductors. The ohmic conductors are the ones that act according to the Ohm's law, right? That says that the potential difference across the two ends of a metallic conductor is directly proportional to the current passing through it, right? Or the current passing through it is directly proportional to the potential difference. Right? That temperature is constant and other physical conditions. So what he's saying is that, practically saying is that, if I plot a graph of voltage against current, that as I increase the voltage, the current in the circuit should also what? Increase, right? But we also see that for resistors, since it's only converting electrical energy to heat energy, what we notice in the process is that guy begins to heat up, right? So it's the one component of the device that can heat up. Does that make sense? Okay, so we see that as that resistor begins to heat up, then we see what? That the resistance of that resistor begins to do what? Increase. Does that make sense? The higher the heat in the resistor, the higher the resistance to, the higher the opposition to the flow of current. So because of that, more energy is needed to drive more current. Does that make sense? So that's why the graph is like this. But for non-ohmic conductors, an example of non-ohmic conductors, we have ohmic conductors, we have our, what do we call it? Our resistor. What do we call that kind of resistor? The ones that have a constant resistance. I think it's constant resistor. Okay. Then our non-ohmic conductors, we have rheostat, right? We have rheostat, we have lead. Is that okay? And we have even diode itself. Is that okay? Okay, it's a type of diode anyways. So we also have thermistors. Thermistors are also non-ohmic. Is that okay? Thermistors, they are non-ohmic. Okay? So the point is this: for non-ohmic conductors, what you see, especially for diode, for example, a diode, the more there. All right, let's go. So for non-ohmic conductors like a diode, for a while the current is going to voltage to current. The current is going to increase as you increase the voltage, as the voltage increases. But after a while, we're going to see a steepness like this, so that even as you put in more voltage, as the voltage increases, it translates to only very small amount of current. It doesn't give corresponding amount of current. Is that okay? So this graph represents the graph of what? Non-ohmic conductors, while this one is for ohmic conductors. All right. So another thing we'll see under resistance is how we conduct. Okay, no, there are even two types of resistance. There are two types of resistance. We have the internal resistance and external resistance. Well, you can call the external resistance as the resistance of the conductor. Is that okay? So conductor resistance. But it's basically external. It means internal resistance simply means resistance of the internal circuit. The internal circuit is, because these are circuits. These are circuits. So the internal resistance is the resistance inside the cell. Is that okay? The resistance of the cell is of the battery is our internal resistance. Because every cell has some degree of imperfection. Is that okay? And what we mean by imperfection is that there's going to be an opposition to the flow of current that is as a result of so many things, either because of the kind of material that it is made of, other things that determine the internal resistance. Let's talk about internal resistance. Is the opposition to the flow of current within the energy source itself. Internal resistance, the opposition to the flow of current within the external source itself. Is that okay? So let's call it small r. We always use small r to denote it, do you remember? So it will be equal to what? V over I, right? This time V sub r over I sub r, that is for the current and voltage inside the guy. Do you understand now? Because it has to flow across it, then flow outside to the external circuit. Does that make sense? Okay, now some of the things that determine this internal resistance are, you know, that it is also, we talked about this is an electrochemical cell, right? So an electrochemical cell is going to have metal plates connected together. So do you know also that the distance between these plates, which is of course will determine the distance of this wire, is also determines the internal resistance? Yes, it does. Because do you remember the resistance, the relationship between resistivity and conductivity? Okay, so for a particular conductor, the resistivity of the conductor will be inverse proportional to the conductivity of the conductor. Does that make sense? So, and we know that the relation between resistivity and this thing and conductivity, resistivity and resistance is this. We said the resistance of a metallic conductor is directly proportional to the what? So that's internal resistance. The external resistance, or the conductor resistance, is going to be the resistance of the outside connection, the outside circuit. And that one is given by R is equal to what? V over I. Does that make sense? Now listen, since the conductor is connected parallel, since the voltage source, the power source, is connected parallel in series rather with this, is connected in series with this, the same current will flow through them. Is it clear to you? The same current will flow through them. Is it clear? All right, and I'm going to show you how. Also remember that we can connect resistance in series and in parallel. Before we do that, let's talk about the EMF of the entire circuit now. The EMF of the entire circuit, therefore, will now be equal to what? The voltage of the internal circuit plus the voltage of the external circuit. Does this make sense? So what does this become? E will now be equal to what? What is VR? It's going to be I, which is the same current. I said the current that will flow through them is the same, right? So I R plus I, this V sub R, plus I R. Does this make sense? So E is going to be equal to, since the current is the same, I into bracket what? R plus R. Does this make sense? So that's the EMF in the entire circuit. Now, another thing that you are likely to come across, very likely to come across, is arrangement of resistors. Okay, so I could arrange my resistors. We can have what we call a parallel circuit, or we always define circuit usually with respect to the arrangement of the resistor or the load. Is that okay? Because everybody knows your voltage should be arranged in series. Is that okay? So, but what determines how your system will be is how you arrange your load. Now, if you arrange, the best way to arrange your load, who can tell me? What's the best way to arrange your resistors? Is it in this arrangement that I'm showing you, or in this second arrangement? What's the best way to arrange your load? Here will be R1, R2, R3. R1, R2, R3. Who can tell me the best way to arrange the load? The first way, the second way. Okay, now let's analyze. If we arrange our load this way, we call this in what? Parallel. Are you with me? Okay. We call this what? In series. You see what the best way is to arrange your load now, or your light bulb. So you are going to understand why sometimes in the house, or you connect wire to batteries. Battery to, you can use wire to connect battery to bulbs, different bulbs. Some will be some will light up well, it's okay, brightly, will shine brightly. Others will be dim, will be dimly lit. Now look at this. In parallel, what are we going to have? It's going to be 1 over R, the equivalent resistance is going to be what? 1 over R equal to what? 1 over R1 plus 1 over R2 plus 1 over R3, or up until what you have, whatever you have, just like we did capacitors. Then for this one, our resistance here is going to be what? R1 plus R2 plus R3. Are you with me now? So which one is going to give us a higher value of resistance? The second one, right? So it means that the best way to arrange your load is in parallel, because this one minimizes opposition to current. Does that make sense now? This one does what? Minimizes opposition to current. While this one, if you arrange bulb like this, you try, we would have tried the experiment. If you arrange bulbs like that, in series, use a wire connect to the next bulb, wire connect to the next bulb like that. You are going, except the voltage is so high. But if you are using your common batteries, your common DC, you arrange in a DC, you see that all of them will be dimly lit. They will dimly lit. Albeit the same current will flow through them. But what will be different? The voltage that will flow through them. Do you understand? Is it clear? The only reason, okay, so let me explain that now. Let me explain, because questions come out from that. I'm angry too. So he said, if I arrange my components this way, we'll call it parallel. And if I arrange this way, we call it series. Now, in this place, into R1, R2, and R3, in this case of parallel arrangement, the current that will flow will be different. The current that will flow will what? Will be different. But in this case, the current that will flow will be what? The same. So same current through. I'm going to explain with something that will make you understand very well. Here, the voltage that will flow will be the same. Is that okay? The energy of flow will be the same. But here, the energy of flow will be different. Why? Because some energy will be left here. The remaining amount of energy will be what will transfer here. Do you understand? The remaining amount of energy will transfer here. Does that make sense? But let me use this conduit, for example. This water hydro system that we normally talk about. If you connect channels like this, and you connect channel like this, or maybe it's not even smooth. If you look at the thickness of this is water going into this place. Is that okay? Water going into this place. So you see, if you look at the thickness of these things, of these pipes, are they the same? The diameter of the pipe, the diameter of the pipes, are they the same? They are not. They don't have equal diameter. So it means that the amount of water inside here will be what? The amount of water, just the amount of water first is what? Is different, isn't it? Are you with me? Yes, the amount of water inside these systems will be different. Okay. How about here? The amount of water inside here too will not be the same because they have different volume. Is that okay? But now, listen now. So, if water enters here, where will it be easier for Okay, first, you know that in this system we say current is the same, and current is different, but here current is the same, right? So which one does it look like? This one look like this one, right? So we say current is the same. And why is that? Yes, because before water gets here, water must pass through here. Before water gets here, water must pass through here, right? And before water gets here, water must pass through here. So it's the amount of water that this one delivers that this one will take. Does that make sense? So it means that what is current? The rate of flow of charge, right? So the rate of flow here, once this guy fills up, by the time it flows into here, to first make sure to fill up this place, do you understand? And be releasing this one small. Do you get it? And it's the amount of this one, the amount at which this one is delivering it. The rate at which this one is delivering it is the rate at which this one will be giving this guy. Do you understand? Because it's the same system, long system. Is that okay on a straight line? But in this case now, the current is going to be different because number one, the rate of flow will be different. Here we said the energy will be different here because by the time water gushes here, because of the, let's say the amount of hose that is supplying this place has the same diameter. By the time water enters here, by the time it enters here, it has to first fill the energy with which it will fill up will be less. Do you understand? It starts to fill this place up. When it fills up, it's not start transferring here. Do you understand now? So it's that amount of energy that is remaining that this one will first receive, then to now continue to flow with that amount of energy. Do you understand now? Unlike in this case, where when the water jet is comes out, what happens is by the time you just get it just spread. Nobody is affecting who, but the quantity per time that is entering each one will be different because they have different volumes. Is that clear? Are you with me? So that's why currents here will be different, but the voltage across them will what? The same. Are we clear? Yes, sir. So that's what explains it basically. Yes. Resistance? I know that thing's confusing. Where did you see? Open it, please. Okay, so listen. So someone just corrected us on something. The resistance is directly proportional to the length, but inversely proportional to the area. Exactly. So resistance will be equal to rho L over A. Is that okay? Please don't let this thing confuse you. How do we explain this? How do we explain this? And it makes sense. Look, let's think of resistance. Listen now. If this was a road that cars are passing, as far as cars, if there are stumps on the road, if this was a smooth road, what will happen if daddy wants to move? Boom, at a very good fast speed, right? So father can move smoothly. But if this guy had stumps like this, he will begin to, maneuver his way around these stumps, isn't it? He cannot just go freely like that. Is that okay? So that's what resistance is. So for him to be able to go, it's easier to maneuver when the road is larger. So when the area is larger, the resistance will be what? Low. And when this thing is longer, the resistance will be what? Higher. Is that okay? The longer the wire, the what? Please don't make the mistake. I know that thing is confusing. It's confusing. Okay, let's analyze capacitor again. Capacitor is direct proportional to area. It should be the opposite. Because resistance, you remember that this one, I told you it was the opposite in the arrangement. In parallel, is like this. But the parallel of this is like the series of this. Do you remember? So please don't forget it. Don't forget it. So you see they are inversely proportional. Eh? Please, So resistance is directly proportional to, but inversely proportional to, okay. So when we said internal resistance there, it means that the longer the wire that you use, the higher the resistance, the larger the space between your electrodes inside the, are you envisaging what I'm saying, what I'm talking about? The larger the space between your electrodes, what will happen to the resistance? The higher the resistance. Is that okay? Do you understand what I'm saying? Okay. All right. So that's that. For resistance in series and resistance in parallel, or basically circuit in series and circuit in parallel. Okay. So we've done this. Now let's now talk about some electrical components before we solve questions. Let's talk about, okay, no, we can't talk about electric components yet. Let's talk about what is called the meter bridge and the Wheatstone bridge. Is that okay? The Wheatstone bridge and the meter bridge. Okay. Now, the Wheatstone bridge, how do you spell Wheatstone bridge and the meter bridge? So they basically work by the same principle. Is that okay? They work by the same principle. Now, in a Wheatstone bridge, there is a system of conductors arranged in a particular way. Is that okay? So we're going to have something like this. Okay. So what we'll now do is that we'll now connect a galvanometer across these two ends. Of course, this galvanometer we are connecting, we're going to connect it and make sure we find what we call a balance point. We call what? You see this balance point too. This, you see this thing I'm drawing here, these wires I drew here. The length of the wire also matter. Is that okay? You know, length of wire now affects the resistance, right? So the length too matters. So it's not just that we're connecting anyhow. We've used this galvanometer to find a balance point between these two systems. So what we use the Wheatstone bridge to do is to find the resistance of a given resistor. When we connect this way, we find the balance point. The balance point on the galvanometer is the point of no deflection. When the galvanometer is reading zero mark, it's on the zero mark. Is that okay? When there's a scale here, there's a scale here. Is that okay? This is your galvanometer, there's a scale here. So when it's on the zero mark, that is when it's on the balance point, the point of no deflection. So now, if this guy, if we get the balance point to be at this point and at this point, if we arrange the system correctly, it is found that the ratio of, if this was R1, this was R2, and this was R3, and this was R4. It was found that the ratio of R1, you can now connect this way. So it is found that the ratio of, you can also connect this. I don't want it to be a straight line wire, so you not think. You can connect it this way too. Is that okay? Is any way we can find a balance point. Does this make sense? It doesn't have to be a straight wire running through. You get what I'm saying? Okay. So we just want to connect our galvanometer and see where is this thing going to be. Where is the balance point going to be? Once we find the balance point, at the balance point, the ratio of, listen now, at the balance point, the ratio of any two ratio that you combine is perfect. But usually we combine ratios across the bridge. Is that okay? So we can combine R2 and R3, R1 and R. Does that make sense? And the way you combine it is the way you should combine. The way you come, for example, is do R1 over R4. How will I do this one? R2 over, exactly. If I combine this way, R3 over R2, you get me? Is that okay? Now, it doesn't mean that, I think if you combine R1 over R2, you should get the same answer. If you combine this and this, you combine this and this. Is that okay? But usually, it's more appropriate to combine across the bridge. Is that okay now? Do you get me? Okay. So that's the Wheatstone bridge. So if we are giving the resistance of R1 maybe to be 2 ohms, resistance of R1 to be 2 ohms, resistance of R2 we don't know, resistance of R3 3 ohms, R4 4 ohms. The way you get R3, let's try that. 2 ohms resistor, R sub X or R2, let's just call it R2. Then R4, say 4 ohms. Are you with me? R3, say 3 ohms. If you have something like this, how do you get R2? R2 will be equal to, you know that R1 over R4. Let's say 2 over 4. You see, I'm connecting across now. Take ratio across. Then it will be equal to R2 over 3. Then you cross multiply, you have 2 by 3 over 4. That is R2. So R2 equal to what? 6 over 4, which is what? 1.5 ohms. Does that make sense now? All right. Okay. So that is our Wheatstone bridge. Now the second one is the meter bridge. Now the meter bridge is exactly the same. But the difference is this. I mean, the connection or relationship is exactly the same. But the difference now is that a meter bridge uses a Constantine wire. A Constantine wire is a wire that the length varies directly with the what? Okay, we're supposed to use that to remember now. We're supposed to use that to remember the formula. That formula, this formula we messed up. We're supposed to use this thing to remember. You remember a Constantine wire. We said it's a wire that what? That the resistance varies with the what? With the length. Varies directly with the length. And we call it meter bridge because the length of that wire is always what? 100 centimeters. Do you get it now? So please don't mess it up. Is that okay? If you forget, just remember other things that are connected with resistance. Is that okay? Such as a Constantine wire. Right, so for a meter bridge, we have 2 resistors here. Let's say we don't know this one. Let's call it R sub X. Then we know this one, known value. Let's call this one. Let's just call it R1. It's known. The value is known. Are you with me? The value is known. Now, you will connect voltage just like this. Now, what you now do is this. You will now connect a Constantine wire in between like this. And the length of this is going to be what? 100 centimeters, isn't it? Or 1 meter. You will now connect just the same way we connected the galvanometer across like this. You will also use a galvanometer to separate them. Do you understand now? You use a galvanometer to separate them. But this is the difference. You will now connect a jockey. You connect what is called what? Now a jockey is just another wire this time that you're using to find a balance point. So you know this is connected to your galvanometer. This is jockey. You now use that jockey to find a point on this wire where the deflection on this guy was 0. So at that point we call it what? Balance point. Let's say when you connected your jockey, you got your balance point here. This balance point, this guy is going to have what? Length L1. It's going to have a particular length, right? Then this point here, you will not be given the second length. What will it be? 100 minus. Does that make sense now? We can call it L2 too. Is that okay? But it's actually 100 minus L1 because it's always 100 meter long, the Constantine wire. That's why we call it a meter bridge. Exactly. So the same way we did that one, we can say that we have that R1, we can take the distance across bridge, RX. Okay, let's also use R1, R2 first for now, so that you understand it. So R1 over R2 is going to be what? L1 over L2 and 100 minus L1. Does this make sense? Is it clear? And if that's the case, you now to prove that what I'm saying here is correct, let's quickly prove it mathematically. That the idea is the same. See, let's call this L2. This is just saying that R1 over R2 is equal to L1 over L2. Okay? Now, it also means that R1 L2 is equal to what? R1 L2 is equal to R1, R2, L1. Okay, is this clear? So what this is saying is that if I decide to divide by L1, for example, and if I divide by L1 over L1 over L1, I divide by L2 over L2 over L2, L1 cancels L1, L2 cancels L2. So it means R1 over L1 is equal to what? R2 over L2. Do you see it's exactly the same? Did you see that now? So either ways you combine it here too. But make sure you combine the same order. So for example, I can combine this and this. How should I combine this? Do you understand now? Is it clear? Okay. So for a meter bridge, you see the questions on that here are very simple. And we've done it in class here. So that's just the case. That's just the case. But just know that you'll be given only one length here. The other length will be found by what? Subtracting from 100. Is that clear? Okay. So that's that. So we are done with that. Okay, then the effect of electricity. Effect of electricity. Now, we have about 4 major or 5 major effects of electricity. And that's what will lead us to the next this thing. Should we solve questions under this? Okay. What's it? A voltaic cell rather. Or galvanic cell. That's another word. Is that okay? Uses what and what? Zinc and copper electrodes. Is that okay? Okay. The Daniel cell. A Daniel cell uses carbon electrode and zinc. Use what? Carbon and zinc. Is that okay? Okay. And the zinc is going to be the what? The negative, right? Carbon will be the what? The positive. Yes. Carbon is positive, zinc is negative. Because the negative is the one that delivers current to the other guy. Do you understand? Okay. We also have the Leclanche. The Leclanche cell uses zinc, which is also what? Negative, right? Okay. And carbon rod in mixture of manganese. So carbon rod in MnO2. Is that clear? Then the Daniel cell. Okay, we've mentioned Daniel. So Daniel cell uses what? Zinc and carbon. Okay. Okay. So are we good now? All right. Pause it, please.
Question 1. In the circuit above, the resistors 2 ohms, 4 ohms, and 12 ohms are connected in parallel. The current through the 12 ohms resistor is. Based on our former knowledge that if resistors are arranged in parallel, same voltage will flow through them, meaning 12 volts will flow through the 2 ohms resistor, the 4 ohms resistor, and the 12 ohms resistor. And recall that V equals IR. Since same voltage will flow through them, we have 12 equals, we are looking for the current through the 12 ohms resistor. So I times 12, and I equals 12 over 12. I equals 1 amp. Question 2. In the circuit, the ammeter reads a current of 3 amps when R is 5 ohms and 6 amps when R is 2 ohms. Determine the value of X. Neglect internal resistance of cell. So we are first going to resolve the resistor in parallel. So we have 1 over R total equals 1 over R plus 1 over X. For when this r equals 5, we have 1 over r total equals 1 over 5 plus 1 over x. Collect the LCM. The LCM is 5x. 5 in 5x, x plus x in 5x, 5. So 1 over r total equals x plus 5 over 5x. R total now, we'll take the inverse, equals 5x over x plus 5. When this r is 2, 1 over r total equals 1 over 2 plus 1 over x. Also, we are going to take the LCM. We have 2x, 2 in 2x, that's x, plus x in 2x, that's 2, equals 1 over r total. So r total now equals 2x over x plus 2. To get the current, to get the voltage, we have V equals IR. Recall that if resistors are arranged in parallel, the voltage will be equal. So V equals V. The voltage that will pass through this circuit when current is 3 amps will be equal to the voltage that will pass through the circuit when current is 6 amps. So V equals V. So we have, when the current is 3 amps, this is the resistor, and V equals IR. So we have 3 times R. Our R is 5x over x plus 5 equals, when the current is 6 amps, 6 times our resistor, 2x over x plus 2. Yeah, equal. So we have 3 times 5x is what? 15x over x plus 5 equals 6 times 2x is what? 12x over x plus 2. So we are going to cross multiply here, and we have 15x into bracket x plus 2 equals 12x in bracket x plus 5. We can see that 3x is common to both sides, so we say divide both sides by 3x. 3x here 5, yeah. 3x here 4. So we open the bracket with these numbers. We have 5x plus 10 equals 4x plus 20. So we basically collect like terms here. 5x minus 4x equals 20 minus 10. 5x minus 4x will give us x, which equals 10 ohms. The value of our x is 10 ohms for question 4.
Number 3 question. 60 ohms over x will be equal to 25 ohms over 100 minus x. So we are going to cross multiply. We have 25x equals 60 into bracket 100 minus x. 25x equals 60 times 100 minus 60x. So we collect like terms. We have 25x plus 60x equals 6,000. 25 plus 60, that's 85x equals 6,000. We divide both sides by 85. S equals 6,000. 70.58. So approximately 70.6 centimeters.
For question 4, calculate the EMF of the cell if its internal resistance is negligible. We are given the current flowing through. The current flowing through is 4 amps, and these two resistors are in parallel. So to get the EMF, we call that V equals IR, or let's just say E. E equals IR. To get the EMF, we must first get the total internal resistance, the total resistance rather. Sorry. Well, we must first get the total resistance. So we are going to resolve the resistance in parallel, and we have 1 over R equals 1 over 3 plus 1 over 6. LCM equals 6. 3 in 6, 2, plus 6 in 6, 1, equals 3 over 6 equals 1 over 2. 1 over R equals 1 over 2. Then R equals 2. We take the inverse. Since we've gotten the total resistance now, we are going to plug in the value in this equation. So we have E equals, our current is going to be 4 amps, 4 times 2. Then E equals 8 volts. That means 8 volts is the EMF of the cell.
Good. Alright, Emuti, come and solve number 5. Emuti, come and solve number 5. Number 5 says a conductor has a diameter this. So the diameter of the conductor is 1 millimeter. So, and the length is 2 meters. So you see here that there is a discrepancy in the unit of the length and the unit of the diameter. So you have to convert, yeah? So we convert millimeter to meter. Or what do? We divide by 1,000. Is that okay? Divide by 1,000, you're going to get 0.001 meter. Does that make sense? 1, 2, 3, 0.001 meter. So then it says, if the resistance of the material is this, so just follow as I'm solving, write all your parameters for first. The resistance is 0.1 ohms, it says. Its resistivity is what? So we're looking for rho is what? Recall that, please don't make the mistake, recall that resistance is equal to what? Rho L over A. Rho L over everybody. Rho L over, so you can see now. Okay, let's go. So, so teaching is not hard, honestly. So rho will now be equal to RA over L. Does this make sense? But in fact, we've not gotten a value for our A. Is there A in our guy here? There's no A, right? So because our guy, the wire, is going to be cylindrical. It's going to be cylindrical in shape, right? So the surface area is going to be what? Pi r squared, which is the same as the area of a circle. Does that make sense? So that will be pi r squared. We're not giving r here, are we? We are giving diameter. Recall that r is diameter over 2, right? So we can solve that here. That becomes area will be pi d over 2 all squared. A becomes pi, which is 22 over 7 times d is what? 0.001 all squared over 2 squared is what? 4. Okay, so A will now be equal to 22. So it's a conversion that got you in error. 22 times 0.001 times 0.001. 22 times 0.001 times 0.001. 0. And divide by 28 immediately. For this stop, right? 2.2 times 10 to the power minus 5. Well, that makes sense now. Very easy to solve. Divide by 28. So area will be equal to what? The first place. Should give you 1 point. No. Yeah, 7. Thank you. Point minus 7, right? Okay, we'll now bring this guy into the equation. So our rho will now be equal to r, which is 0.1, times a, which is now 7.8 times 10 to the power minus 7, over length. What is length? 2 meters. So we say divide by 2. Divide here by 2, we get 3.9, right? 3.9. So we get 0.1 times that. That gives us we'll just add minus 1 to that one. Rho equals to 3.9 times 10 to the power minus 8. What's the unit of rho? That will be ohms meter. No, ohms meter squared. So ohms meter now. Because meter will cancel meter. So ohms meter. Alright. So that's the answer. Is that clear? Alright, so we'll come and solve number 6. Let's do the first one.
Question 6. Calculate the rectangular required to balance the grid in the circuit cabinet. So, calculate the guidance. R4 over R1 equal R over R2. We are looking for this R. So, it will be 15 times 24. So we say R4 is 20 and R1 is 15, R2 is 24. So we multiply R2 and R4, R1 and R2 over R4 equal 50 times 24. 360 divided by 20. R equal 18. So R4 is 15, R1 is 20. So multiply R4 and R1 divided by R2. Divided by R.
So 18 what? Volts. 18 ohms, mama. Okay, so we solve the last one for us. What's the last one? Who solved number 7? None of you. Or did you don't attend this at all? Okay, number 7 says, please, Uti, go and give this to No tool. Go and give it to this thing to help us charge. Get the charger from my phone, my bag. Alright, let's go. Fast. Bend. Okay, so we said that number 7 is a cell of internal resistance R supplies a current to a 6 ohms resistor. So internal resistance R is R, right? And also it supplies to a 6 ohm resistor, that's external resistance, right? Or resistance of conductor. And its efficiency, the efficiency of that cell is 75% efficiency. And recall that efficiency is output over input, right? But the output now is not a measure of 75%. The output now is not a measure of the resistance it's supplying, right? It's a measure of voltage, right? Does that make sense? So what it's saying here is that if it supplies 75%, find the value of R. If its efficiency is 75%, it means that it delivers 75% of the EMF. It delivers it outside, right? And this 75% of the EMF is going to be the I times this. Does this make sense to all of us? Is it clear? You're with me, right? Wait, let's just write, since internal resistance is involved, you remember E equal to I into bracket R plus big R, right? So it means that the total EMF, no, this EMF now is the amount that is delivering outside. So the total EMF is not given yet. So this one is the voltage, this 75% is the voltage for the outside circuit, voltage that is reaching the outside circuit, right? So I have 0.75 of the total EMF. Does that make sense? Okay, so 0.75 of total EMF is I times 6 or 6I. Okay, so it means that the remaining EMF, that will be 0.25 EMF, is one that is being supplied to the internal current, or that is being opposed internally, right? So that will be equal to IR. I is the same because they are in series, right? Good. So since I is the same times R, okay, let's just get what I is here. So I is going to be what? And more like let's put equation 1. Let's put them in equation. Equation 1 over equation 2. Do you get me now? If I do that, equation 1 over equation 2, this over this takes care of this here 1, this here 3. I takes care of I. So 3 will now be equal to 6 over R. R will now be equal to 6 over 3. R equal to 2 ohms. Is it hard? Alright. So now let's go to the next part. You know, we've not discussed. I saw a question here. It says that answer this question for me. Which of the following instruments will accurately measure the EMF of a cell? No. Potentiometer. Is that okay? Potentiometer. But we did not discuss how a potentiometer works. We only discussed Wheatstone bridge and meter bridge, right? Let me pause it, let me coin the word and let's quickly discuss it. Then we'll also now talk about conversion. Now the potential, now we know that there are more accurate measures of there are more accurate measures that we use. There are more accurate measures that we use for getting this thing. But you see that question asked for the very old ones, the ones that have been ammeter, moving coil ammeter. A moving coil ammeter is called what? Galvanometer, right? A moving coil ammeter is a galvanometer, ammeter itself, voltmeter. So all these guys and potentiometer, those are the guys that have been since the 18th century. You understand? So now there's a man named Pogendorf. Who can tell me what his second name is? Guess. Christian. Christian Pogendorf. So he was one that designed this technique of do you understand? That one to that Wheatstone. His name is also Wheatstone, I've forgotten his name. Was one that designed the system for solving, determining resistance. Is that okay? So this guy now suggests that if you want to calculate the EMF of a cell that is unknown, so put a standard cell that you know the EMF. Is that okay? Now connect a wire, a meter long wire too. Is that okay? But this one, I'm not sure it's a meter long, but usually I think even with the experiments we use a meter long wire. So that's why I'm saying meter long, a meter long wire. Is that okay? In physics practical, is it not long, meter long we use? So connect with a meter long. Now connect another EMF in parallel. Would this be parallel? Another EMF. You want to, so the one you want to determine is this one. Is that okay? No, the one you want to determine is this one, sorry. The one you connect to a galvanometer is the one you want to determine. Is that okay? So you connect this guy to a galvanometer, then you now use a jockey again. A jockey is just the wire you remove. Is that okay? So you use a jockey to find the what? A balance point here, which is the point of no deflection. So that point of no deflection is the point where no EMF is read. There is no deflection of this galvanometer. Is that okay? So with that, is that point you use to determine this. So it is such that the EMF of the standard cell over EMF that you are trying to determine, maybe U2, is going to be ratio of L1 to L2. Is it clear too? Is it hard? No, at least mathematically it's not hard. It makes sense, right? Okay. Then I said we're going to discuss something else. Conversion, thank you. So how do we convert? We can use a galvanometer to measure EMF. But you see that question said accurately. Is that okay? So how do we use EMF galvanometer to measure voltage? And how do we use the galvanometer to still measure current? This is way we do it. We convert the galvanometer first. Yes, thank you. Galvanometer to what? To ammeter to measure what? Current. Then to measure voltage, you convert galvanometer to what? To voltmeter or voltameter. Is that okay? Now, if you convert, this one is very simple. To convert galvanometer to ammeter, you connect a low resistant wire. We've talked about it before, right? You connect what? A low resistance wire called shunt. Is that okay? The system, the galvanometer will be called a shunt galvanometer. It's just a wire that has low resistance. You connect it to this. Now, in parallel. Somebody say in parallel. In parallel. In parallel. In parallel. In parallel. Connect it in parallel. So galvanometer to 1 meter. You connect a low resistance short in parallel to this guy. So if our galvanometer is here, either one you draw, you connect a low resistance shunt in parallel. Is that okay? If you connect a low resistance shunt in parallel, let's analyze the system. What will be equal here? What will flow through them that will be equal? Voltage will be equal. Is that okay? But current will be different. So that one that is different is the one we analyze. So the current through the galvanometer, let's call it IG. Do you remember now? I sub G. And current through the shunt will be I sub S. Is that okay now? Right. Then voltage through both of them will be V. Does that make sense? Does that make sense? So if voltage is the same for both systems because they are connected in parallel, then voltage in the galvanometer will be I sub G times R. Is that okay? And the voltage, this R sub G too, is that okay? and the voltage through the shunt, what? I sub S times R sub S. Does that make sense? So you now say that the formula of what? I sub G, R sub G equal to I sub S, R sub S. Why? Because voltage is the same across board. Is this clear? Who is not clear with it? Okay. Then to convert galvanometer to voltmeter. For galvanometer to ammeter, you connect low shunt in parallel. Low shunt in parallel. Low. Alright, but to convert galvanometer to voltmeter, you connect high shunt in series. Just equal and opposite, opposite, right? You connect what? High. Now we don't call it high shunt. We just say high resistance. Is that okay? High resistance wire in series. Thank you. In series. Is that okay? So if you connect in series, you connect high resistance now in series with it. What will be equal and what will be different? Current will be equal, voltage will be okay. So current through the galvanometer is current. Current through the high resistance wire is what? I2. Current in galvanometer I. Current the same. Does that make sense? But the voltage through the galvanometer what? V sub G different. Voltage through the high resistance what? V sub R different. Does that make sense now? Okay. So since this one is the same, we can easily say, you know the way we equated that time. I here is going to what? V sub G over what? R sub G. In this case, V sub R over what? R sub R, right? So we can therefore say that V sub G over R sub G is going to what? V sub R over R sub R. Does this make sense? Okay. Okay. So, but this one, when you connect it, we say we call this one a what? A shunt galvanometer. You call it the what? This one you call it a multiplier. You call it what? Multiplier. If you say you forget things, it's just because you've not revised. It's because you've not revised. If you have revised a lot, enough rather, you will remember all these things. Now, before we go to heat, let's quickly do some questions on resolving. Is that okay? Resolving circuit? I saw many questions here. I'm just interested. So that if you see a problem with resolving circuits, hey, you understand what I'm saying now? Let me pause it. Let's just quickly resolve like 2 or 3, or 4. 3. Let's do 3. The symbol is this. It's called omega. It's called what? Omega. Okay, let's go. There's also a Greek alphabet. All right, let's go. The first one says 5 ohms. It's like this, right? So you resolve from one junction to the other. You resolve between junctions. Do you understand? More like junction to junction. Is that okay? You resolve from junction to junction. Resolve from. So now, for example, where is a junction here? This is a junction here. It separates this. This is a junction here. It separates these two systems. So anyone that lies within a junction, you resolve them first. So for example, this one that lie within a junction, resolve them first. What's wrong? Headache. Sorry. So in this case, they are in parallel because they are separated by junctions. So they'll be in what? Parallel. So because they are separated by junctions, they'll be in parallel. So we have 1 over R equal to 1 over R1 plus 1 over R2. Is that okay? They lie within the same. Or another way to just be is this. Once you see that there is a diversion, see there is diversion here, you will know that current here is going to be the same, but voltage will be current here is going to be different, but voltage will be the same. You do understand now? Flow rate will be different once they divert. Is that okay? So parallel. So we have 1 over R is equal to 1 over 3 plus 1 over 4. Now I've told you the trick for this one. If you are doing two guys, if you are doing just 2 guys together, just say 3 times 4, 12 over 3 plus 4, 7. This is what I did. The product on top, if it's only 2, it's not 2, it doesn't work that way. Alright. So this becomes these ohms for this guy. So our system has now been resolved to this. 5 ohms to these two places. I resolved it to 12 over 7 ohms. Does that make sense now? So you now resolve this now in what? Series. It now becomes R equals R1 plus R2. This becomes R1, 5 plus, here is 1 ohm number, 5 over 7. That becomes 6 ohm number, 5 over 7. Yes, now, here, 1 over R is equal to 3 times 4, the LCM, 12. 3 and 3. Do you understand? Inverse. Exactly now. So this becomes 6 ohm number 5 over 7 ohms. You can convert this to decimal if you care, if your option is there. Is that okay? Alright, for number 2. Which one should I solve next year? You will solve the rest. I solve number 4. I didn't complete the question. Let's say 2 ohms here. Let's say 3 ohms. Let's say 4 ohms here. Which one should I solve? Question 3 or 4? 4. To do this one now, I'm going to explain how you do the rest. So let me do 4. Is that okay? So where is junction here? Where is the first junction here? If you are going like this, where is the first junction you encounter here? Here, right? You are going like this because from positive, conventional current flows from positive to negative, right? So current to first encounter this junction. So there is separation here. So it means this one and the next guy are in what? Parallel. But this guy and this guy in what? So let's resolve them together first. So if you want to resolve these two, it becomes R equal to what? 3 plus 5. That 2. That what? 5 ohms. That will be for this case. So our system has now turned to, our junction is like this. We now have 5 ohms here. Does that make sense? And another 3 ohms here. Then, so there's a junction here again, right? Good. There's a junction here. There is one rule called the Kirchhoff's rule, or Kirchhoff's rule. Do you remember it? That the sum of current that enters a junction is equal to the sum of current leaving the junction. Does that make sense now? Total current that enters a junction, look at it. Total current that enters this junction from this place, total current that enters will be equal to the total current that will leave here. So the current that will leave here is going to be I1 plus I2. Does this make sense? That will flow into any guy that is connected here, such as this. Is that clear? Okay. So what do we have here? This guy is in parallel, this guy. So we have 1 over R will be equal to 1 over 5 plus 1 over 3. Using the trick I just taught you, R will be equal to what? 15 over, is it clear? For just 2 guys. Okay. This becomes in ohms, okay? So that guy now, so this whole thing now, will now be in series with this guy. Do you agree with me? Will now be in series with this guy. So this guy plus this guy will now be our R1 plus R2. That will be 15 over 8 plus 4. What does that become? 15 over 8 is what? 2 or 1 over 7 over 8 plus 4 plus 5 over 7 over 8 or 5.875, right? Ohms. Isn't it? Isn't it? 7 over 8 is this one by now. Okay, are we good? Alright, so solve number 3 and number 2 and leave your answer in the comment section. So you see this guy now. To solve this guy, this and this, they are in what? Parallel. Capture them as parallel and then the rest series. Do you see that? This next one, parallel, right? The rest in series. Because if you see here, there are only 4 junctions here. One junction, one junction, one junction, one junction. Is that okay? Once you collapse this junction, then the rest are in what? Series. Is that clear? Alright. Let's go to the next thing. Now the next thing is the heating effect of electricity. Are you with me? The heating effect of electricity, and we have to talk about electrical components. Is that okay? Now the heating effect of electricity now is how we measure how much this thing power you are consuming in your house. Is that okay? That's how we measure how much power you are consuming in your house. Now remember that heat energy or energy is going to be what? QV. Do you remember? Is this clear to everyone? Okay, do you remember this one? You remember we said electric potential is equal to work done per unit of charge. So by the time you correspond by. You now get now? Okay. So and work done is energy. So heat energy to can be calculated this way. Does that make sense now? Okay. So we now know that work done is equal to Q. Recall that Q is equal to what? IT. Do you remember? So therefore our work done becomes what? Or heat energy. Let's change it to heat energy here. Current times voltage times time. Does that make sense now? Or current times time times voltage, either way. Okay, but this is the convention. So also recall that V takes the form IR, right? So heat is going to be equal to what? I squared I times IR times T. That becomes what? I squared RT. In fact, this guy, Joule's law of energy conduction here, states that the total heat energy consumed or total amount of energy consumed, electrical energy, is directly proportional to the current, square of the current, and the resistance. Is that okay? And the time over which it was consumed. Does that make sense? Okay. So another one thing we can do here is that I is V over R, right? I recall that I is V over R. So here we can say that heat energy is also equal to what? V over R times V times T. So H equal to what? V squared over R T. Does this make sense? Okay. Yeah, we should now bring in the formula for power, right? So recall that power is equal to rate of work done. So the mic stopped working here. All right, what he's saying is basically power is equal to time rate of work done. So we have IVT, which is the initial formula that we got for work done, IVT over T. So T takes care of T, and we have P, that is power, is equal to IV, current times voltage. That is also what we, from what we already know. Okay. So now, the way the electric distribution companies measure the amount of energy consumed is they measure it according to the amount of power that is consumed, the amount of power that is consumed. So such that they measure it in kilowatt hour. That is the quantity of watts times number of time that we consume it. Is that okay? That's the way the amount of energy consumed is measured. So that is power times time, and the power is going to be measured in kilowatt. The power is going to be measured in kilowatt. So what kilowatt simply means is 1,000. That kilo means 1,000. So if you see something like H equal to 5,000, H equals to 50,000, that is 50 kilowatts. So that's what we have there, 50 kilowatts. Okay, so the question says that the current is about 2 amps and the voltage is about 240 volts that is consumed. So, and the time the voltage was consumed for 3 hours, and the rate at which the energy was charged was 10 kobo per kilowatt hour. So for each kilowatt hour we charge 10 kobo, or 10 kobo is charged. So the first thing to get there is to get the amount of energy that is used and over which time it is used. So we have that energy is equal to IVT. Does that make sense? So that we have it as 2 times 240 times 3. 2 times 240 will be 720. 720 times 3, 48 rather, 480. So 480 times 3, that will be 1,440. You now divide that
by 1000 to get in kilo. So to convert from watt to kilowatt is you divide by 1000, or you basically say if 1 kilowatt, if 1000 is equal to a kilo, then that amount, whatever amount you are given, is equal to x, and then you cross multiply. So here we know that 1 kilowatt hour is charged 10 kobo. Okay, so therefore how much will be the cost of 1.44 kilowatt hour? You know that that 1.44 kilowatt hour was gotten by dividing 1440 watts by 1000, and we got 1.44. Then you cross multiply, you are going to have 14.40 kobo, and that is how to go about solving that question. So I basically listed the parameters here. I'm going to show the question on the screen, or I'll try as much as possible to show the question on the screen. Okay, so now we have the safety devices. Now we have a number of safety devices. We have the circuit breaker. Now safety devices are basically the devices that help to prevent electrical hazards. So those are the safety devices that we have in electricity. The first safety device we're going to be considering is the circuit breaker. Then the second is the fuse. Now the circuit breaker is represented by that symbol that you can see on the board, the circuit breaker. And it is like that because the normal common circuit breaker we use here in Nigeria is basically like that. There's a wire that is connected to one end of a ceramic plate like that. So that ceramic plate is the circuit breaker. So you connect the teeth of the metal that is there on those two edges. Those two edges represent the two edges, the two lines under that circuit breaker. So those two edges have connected to them teeth with which they help to complete the circuit. So we call them circuit breaker because when we remove them, the circuit becomes opened. All right, then a fuse is basically in that that's the way a fuse is represented. Is now the rating. There are various rating of the fuse. We have a 3 amp fuse, 5 amp fuse, depending on the specification of the appliance that the fuse is supposed to be applied. Now you see, the fuse is made up of a thin wire that is connected in a tube that is connected to two edges of that passes through through a tube and has two conducting ends. And okay, that's MCB and ELCB that I wrote are the types of circuit breakers. Now for the fuse, we have for example, if a fuse is rated 3 amps, it means that it cannot permit any current that is greater than 3 amps to pass into the appliance. It means that the appliance the fuse will not allow a current that is greater than 3 amps to pass through. So if there was a current of 5 amps trying to flow through it, what happens is that the fuse will get heated up and will melt rather. It will melt away, and by melting away it has discontinued the circuit. So you can see what I cleaned there. It has discontinued the circuit because it has melted, because a current that is greater than the amount that is permissible to for the wire is trying to pass through it. So because of that, it died. I mean, it's melted away. All right. Now another thing is, so it means that it can only permit, for example, a 5 amp current can permit anything less than 5, such as 3 amps, 2 amps, or 1 amp to pass through, even 4 amps, but will not allow any any current greater than 5 amps to pass through. Now, all of these 3 components we have mentioned so far are always connected to the live wire. Take note of that. The circuit breaker, the fuse, and the switch are connected to the live wire. Now also the switch that is shown on the board there is a two-way switch. A two-way switch. So you see, it's not like the common switch. You're going to see 2 ends there. So my point is this, that the circuit breaker, the fuse, and the switch, they are connected to the live wire. You know, there are 3 types of wire in the circuit. There is the live wire, which is usually red, and there's the neutral, which is usually black, and there's earth. Is that okay? So the neutral has no charge. It has 0 potential. The live has the highest potential. Is that okay? All right. So now let's go to the next topic, which is electrolysis. Electrolysis. Now, what is electrolysis? Electrolysis simply means the chemical process that brings about the electrical a process that brings about the breakdown due to electricity of a particular compound in the solution or molten form of that compound. So electricity is passed inside a solution of a compound so that we can split apart the components that make up that compound. For example, electrolysis of brine, which is NaCl, will involve the passage of electricity into the system such that the brine, that is NaCl dissolved in H2O, will split into Na, sodium, and chlorine. Is that okay? So now there are different parts of the electrolytic cell. Now the major difference between electrolytic cell and the electrochemical cell is that this one, we said electricity will pass into it for the reaction to take place. Electricity will pass into it, so it means that the reaction is non-spontaneous. The reaction is non-spontaneous, and electrical energy is converted into chemical energy in an electrolytic cell. Electrical energy is converted into chemical energy. All right. So now we have 2 types. There are 2 plates. There are 2 plates that are drawn there. You can see 2 plates there, the anode and the cathode. So the one that is connected to that positive end of this thing is the positive end of the battery or of the cell is the anode. Then the one that is connected to the negative end is going to be the cathode. The one that is connected to positive end is going to be the anode. The one that is connected to the negative end is going to be a cathode. Now there are possible questions that you could be asked is, what is the anode? That the one through which current enters into the solution is called what? It's going to be called the anode, because conventional current flows from positive to negative. But the one through which electrons enter into solution is the cathode. The anode is the one through which current enters or electron leaves, and the one in which current leaves or electron enters is the cathode. Now, Faraday's law of electricity says that the mass of an element discharged in an electrolysis reaction is directly proportional to the quantity of electricity that is passed through it. So, and remember that quantity of electricity is equal to IT, Q equal to IT, that is current is rate of flow of charge. So by the time you cross multiply, current is Q over T. So Q will be equal to I times T. So you now bring in the constant, that's Z there. Z is called the electrochemical equivalent. So to restate Faraday's law of electricity, it says that the mass of an element discharged during an electrolytic reaction is directly proportional to the quantity is directly proportional to the quantity of electricity passing through it, provided that the electrochemical equivalent is kept constant. Then Faraday's second law says that if the same quantity of electricity is passed through different electrolytes, that the masses of the elements discharged is directly proportional to the chemical equivalence of the metals. And notice, and the law can also be said that when the same quantity of electricity is passed through different electrolytes that are connected in series, they must be connected in series. Is that okay? So the mass of, or the masses of those of those elements discharged are directly proportional to the chemical equivalence of those metals. By the way, electrochemical equivalence is the quantity of electricity required to discharge one mass, a unit mass of the metal. All right, so that's that about electrolysis. Now let's talk about magnetic field. The magnet or magnetic field. The magnetic field or the magnet. The magnetic field or the magnet. Okay, now we already know that the magnet is gotten from um, the the ore which is known as magnetite, and the ancient China called it lodestone, which meant leading stone. So magnetite has the formula Fe3O4 as it is written there. So it is magnetite. So, and the ancient Greek, they called it leading stone, and this was the reason that a bar magnet that is freely suspended is going to come to rest at roughly north-south direction. As you can see in that my demonstration, you see that the magnet might be staying, the magnet might be horizontal by the time you suspend it. After almost immediately you are going to see it coming to rest at roughly north-south direction. So they saw that it could tell it rotated in the direction of north and south. So because of that, they called it leading stone. So now some substances are classified into permanent magnet or temporary magnets. The temporary magnets are called electromagnets, or another name for them is what? Electromagnet. Now, they are called electromagnet or temporary magnet. So we have permanent magnet and temporary magnet, or yeah, temporary magnet, and they are called temporary magnet because the moment you remove the electrical source, that is the wire that is wound up around them. So if immediately it is removed, what happens is that it becomes demagnetized. It no longer functions as a magnet. So that is that about permanent and non-permanent magnet or temporary magnet. Now there is now the kind of metals that are used for electromagnets. We have the soft iron core. In fact, the soft iron core is well commonly used because the soft iron core is quite flexible. So not necessarily flexible, but at least it's easy to magnetize. It's not that it is actually flexible, it's actually that it is easy to magnetize. So because of that, it is commonly used to make electromagnets. But the problem with it too is that it gets easily demagnetized. So it follows that the faster and easier it is to get magnetized for you for a particular substance, the later it is for it to be demagnetized. So for example, you're going to see steel on the board there just behind me. You're going to see steel. Steel is a substance to hardly, the steel is a substance that is very hard to magnetize, and of course once you remove the magnet, it is also very hard to reprimand. So we have, how do we now make magnets? We have the mechanical method, which are the stroking method and the so basically the stroking method, we have two types of stroking. We have the single stroke and the double stroke. Now in the single stroke, you bring the magnet in one direction, you stroke in one direction. As you bring the magnet, you raise it up. So what if you now wanted to stroke with two magnets? If you stroke with two magnets, the two poles that are stroking must not be the same. Else you would get what is known as consequent poles. Consequent poles. So what you do is that you will if you want to do double stroking, you will stroke with different edges. So if you are stroking on one side with north, you will stroke on the opposite end with south. So that the parts that you are that part that you are that part that you are stroking with north will get the north polarity, while the other part will get the opposite polarity, which is south. Okay. So now let's talk about the hammering technique. The hammering technique is used to, when you hammer a piece of metal at roughly north-south direction, is going to become, you first heat it up, then the heating will cause, the magnetic domains to be adjustable. By the time you now hammer it at roughly north-south direction, we are going to produce a magnet. All right, then we have the electrical method such as the solenoid. Now you see the solenoid I've drawn on the board. Now you're going to see that the current is flowing from my negative. So as you're looking at the screen now, from my left to my right, that's the direction of current. So the direction you stay, where the current appears to be flow, if you follow that solenoid, you know that you know the direction of the current flow. So once you know the direction of current flow, the direction where you stand and it's seen as though current is flowing clockwise to you, that place will be the south pole. And where you stay and you see that place will be the where you stay and you see that place will be the position where you see the current as coming from anti-clockwise. That place should be your north, but clockwise the place should be your south. So if you look at it vividly, if you look at the arrow I drew, if you want to write S, it should look like you are going clockwise throughout. So if I stand to my left and then view that thing, I'm going to see that the current is running clockwise. All right. So that is that for that's why all for magnets and magnetism. Now the next thing is on angle of inclination and angle of dip. Now if you look at that magnet, a straight line drawn to pass through it is called the magnetic meridian. And you know that the magnetic meridian, so remember the experiment first, that when you freely suspend the bar magnet, it's going to come to rest at roughly north-south direction. So you can see what I'm drawing there. You see that it's coming to rest by itself at roughly excuse me. If so, you're going to see the diagram I'm drawing, you see that the line I just drew, the two lines I just drew, the one that is vertical there is the geographic meridian of the earth, and the line I drew where I drew a magnet there that is slanting and it's a line to cut through it, that's not fuse. That's there is going to be the what? The angle between that place, that I said that line that you draw through the magnet is called the magnetic meridian. You now compare the magnetic meridian and the geographic meridian. The angular difference between them is called angle of inclination. The angular speed will be called angle of the angle between them is called angle of inclination. Then the angle between that same place and the horizontal to the plane, horizontal axis, is going to be called angle of dip. Angle of dip. So now we know that the electric field runs inside the magnet from south to north and outside the magnet from north to south. So we already know that B is equal to mu naught I over 2 pi. So we have that vector B is also given by the formula mu naught I over 2 pi. mu naught I over 2 pi. Okay. So we also talked about the magnetic field. You are going to see that the lines are closest together near the magnet, and that point is going to be the point of the highest strength of the magnet. Okay, so
let's go to the motor effect of electricity. We said that in 1820, this man, Hans Christian Ørsted, did what? He discovered the link between magnetism and what? Okay, and electricity. And what did he find out? He found out that a current carrying conductor or a wire in which current is flowing has a magnetic field around it, right? And thus we postulated the first right-hand rule that the magnetic field around a current carrying conductor is such that if you hold the conductor such that your thumb is pointing in direction of current, of course we always know direction of current, that the direction of magnetic field is going to be the direction in which your fingers are curling around the wire. Is that okay? So if I hold this wire like this now, if this wire current was going up the board, then it means that my conductor, we use vector sign, right, to denote the direction. So we know that my magnetic field will be entering into the board at this point, right, and be coming out of the board at this point. Does that make sense? This back represents the back of the arrow. This one represents the front of the arrow. So the magnetic field will be like this, like this, like this. All right. So what that means is that it will be coming out of the board, going like this, and into the board. Do you see that? Okay. So it means that if our current, this wire now is standing straight like this, right? If I made the wire to stand like this, and the wire is looking at us, and current was coming towards us. Current is coming towards us. If current is coming towards us, it means the direction of magnetic field. What? What direction is this? Anti-clockwise. Is that clear? All right. Good. Now that's very good. But there's also the Maxwell corkscrew rule that the direction of cork. So if my cork, what will be the direction of cork if I'm going rightward like this? The direction of cork is, as I'm going, what direction am I going? Anti-clockwise. So what's the direction of this lead? Up, right? Okay, so that'll be the direction of current. Is that okay? But the direction of my hand is going to be what? Anti-clockwise. If my cork is going into it, it means my magnetic field is what? Clockwise. Good. Now, one of the use of that thing is that we use it to measure, we use it to know the direction of the magnetic field. So, but of course, one other thing is that we use it to know how magnetic field lines affect one another. We have first established the fact that B is equal to mu naught I over 2 pi. Does this make sense? Now, we also have established the fact before that when conductors are together, for example, if there's a current, if there's a conductor line like this, there's another conductor line like this, if they carried similar currents, what will happen to them? They will be attracted to one another. Do you remember? If current was going that way, it means the magnetic field will be going into the board here, right? Into the board here, out of the board here, right? In this place too, into the board here, out of the board here, right? So with that, magnetic field will flow together and they will be attracted to each other. Is that okay? The magnetic field will align. But if this one, the current was flowing anti-clockwise, these are still parallel to each other, but the kind of parallel is called anti-parallel or anti-parallel. Anti-parallel because current is flowing in different direction. So here, in this case, if this is the direction of this, and then current will be entering into the board here and be coming out of the board here. Because of that, there will be repulsion. Because current is entering and entering here. Do you understand now? So that's the case. So they will, unlike current, repulsion. Does that make sense now? Like current, attraction. Okay. Now the other thing is now the solenoid system. We've talked about that before anyways. So we know that if I pass a direct current through this wire like this, if I pass a direct current and if I pass a direct current generally, this thing, current magnetic field will flow inside this. Magnetic field will expand because of the coil of wire, right? And if I wanted to make the magnetic field stronger, what will I put? I'll put a soft iron core. Is that okay? Before, initially, what I had was my solenoid like this. Is that okay? But if I wanted and in the solenoid, magnetic field will overlap each other and become expansive, right? And be stronger. So if you also increase the strength of that, put a soft iron core, soft because it's easily magnetized. Is that okay? The second thing to do is increase the number of turns. The number of turns of the wire, the higher the number of turns and closer they are. That's why you have seen a rotor before. You have seen something that the wires around it are much, right? You've not seen that kind of electrical system before. The thing is always tightly close to each other. Tightly close to each other. Alright, so that's the number of turns. So increase the number of turns or put a soft iron core. The reason why a soft iron core helps is also that a soft iron has magnetic domains, right? So its own magnetic domain will align, and because of that, the strength of that thing will be the strength of the solenoid plus that of the iron core that is inserted within. Is that clear? All right. So where will be the north if currents were to be flowing in this way? Where will be the direction? Where will be the north? Where will this place be, north or south? If I have this system, where will north be? Is this north or south? North, south, south, north. Which one is correct? A or B? B is correct. A is correct. B is correct. Okay, let's see. Where's the direction of current here? Here, right? If current is flowing like this here, it means that it's going like this, right? Isn't it? So if you look from this direction, where is this? Clockwise, isn't it? So where you look from and it looks like it's clockwise, that will be what? South. Where you look from and then this place will be north. Does that make sense? Because it's entering through here. My will be anti-clockwise, so that will be the north. Is that clear? I showed you the trick, right? If you want to write N looks like what? Anti-clockwise. Does that make sense? We want to write S. You put your arrows. S looks like what? Clockwise. Do you see it? Okay. So don't forget it all. Who is going to forget? Good. Alright. Now let's go to the motor effect now. The motor effect of electricity is just what happens if there is a current flowing in a current carrying conductor is placed in a magnetic field. So for example, if I have this magnetic field like this, I have my magnet like that. Let's say this was my north here and this was my south here. So magnetic field is towards where? Rightward or leftward? Leftward, isn't it? So magnetic field lines are going like this. Now, in this direction. Now, if a conductor were to be placed here, and now my conductor is connected to a power source here, so meaning that what? Current is flowing through it, right? In what direction is coming from here? Downward or upward? Downward, good. Is this clear? So this is the direction of current. You don't understand what I'm doing? Okay. This is the direction of current. Now, where will this wire move? We discovered that there are two magnetic fields here now, right? Because this is carrying current, it's going to have magnetic field. And is already within a magnetic field. So there will be two magnetic fields that are interacting. What will happen? A force will be created. Is that okay? So where would what will be the direction of current? Welcome, sir. What hand rule do you use? Fleming's left hand rule. Don't forget, motor uses what? Fleming's left hand rule. while AC generator uses what? Fleming's right hand rule. DC motor or AC motor uses what? Fleming's left hand rule. Is it clear now? Only generator uses what? Right hand rule. And what we use Fleming's left hand rule to determine here is the direction of force or motion. Is that okay? In the other case, what do we use Fleming's right hand rule to determine? Direction of current. Direction of what? So also for charges, we're going to get there now. So where will the force move in this direction in this case? This hand represents what? This hand represents what? This hand represents what? Field. Is that okay? So magnetic field is like this. So let's point in that direction. Where's current going? This current hand. Current is going like this. So for magnetic field to be going like that, it has to be like this. Right? No. This field, okay. Something. Jesus Christ. Something like this, right? Isn't it? Magnetic field is going like that, right? This magnetic field, isn't it? Current is going towards me like this, right? So where will the force move? All to get down. No, twisted your hand. Okay. Am I wrong? Are we wrong? You are correct, right? So this wire will move where? This wire will move where? Down. Downward, yeah. And the force on the wire is directly proportional to the product of the magnetic field and the current and the length of the wire. Is that okay? Sine theta. Is that okay? And where theta is the angle between what? The wire itself, so the length of the wire, and the magnetic field. And we said that the closer to perpendicular this wire is staying in the magnetic field, the higher the force. So that at perfect perpendicularity we have what? B equals to F equal to BIL. Is that okay? Where theta equals what? 90 gram naught. Does that make sense? Because sine 90 is 1. Do you remember now? Okay, now if force acts on a wire that is carrying current in the magnetic field, it therefore makes sense to say that force will act on a charge, isn't it? Okay, in the magnetic field too, isn't it? And the magnitude of the force is given by what? If F is equal to, recall that F is equal to what? BIL sine theta. And I, current, is what? Charge, rate of flow of charge, right? Charge flow per time. And L, distance, is equal to what? Speed times, do you remember? Speed times time, or velocity times time. Does that make sense? So if we substitute that into that, that becomes what? B field, yes, times, no, this one, Q over T times VT. Does this make sense? This case takes it, then we have F for F is going to what? BQV sine theta. Does that make sense? Also, the closer the perpendicular, the velocity to charge to B field. Do you understand? There are two vectors here. Is that okay? In fact, this is called the Lorentz force. It's called what? Lorentz. Don't forget. Oh. The Lorentz force. And Lorentz force is given by this. F is equal to Q into bracket vector B cross vector B. Is that okay? You know I'm using cross product so that you understand that if you are given in vector notations like V equal to I 4I 3J and Q equal to, B vector is given by 2I minus 4J. You know how to solve it, right? Do we remember? Yes. Simply take the determinant. So B cross B will be what? Will be what? 4, 3, 2 minus 4. Do you remember? So this becomes, how do you take determinants? This times this is equal to minus 16 minus 6 plus, is it plus or minus? Minus. We're subtracting this from this. No. We are adding the guys. We are subtracting this from this. Okay, for 2 by 2, we are stopping here now, isn't it? All right, so this minus this got what? Minus 22 minus 22. Okay. Is there something we are missing out? Okay, no. It's in 3 by 3 that will bring one out. Is that okay? So if you're just told to find the determinant, just do this by this minus this by this. Does that make sense? So minus 22 will be your vector B, then this will now times Q. Is that okay? Now, if electric field was also in the system, it will be F equal to E plus QV cross B. Does this make sense? It's still an advanced form of Lorentz force. It's called what? Lorentz force. That's the force acting on a charge placed in the magnetic field. Are you with me? Now, what if as it is now? Somebody say as it is now. Now, for a charge in the magnetic field, the force is always causing that charge to rotate. I think I proved that to you, right? Using the law of it's going to rotate. So if it rotates, then it means that it will have a centripetal force. Does that make sense? To have a centripetal force. So centripetal force will be equal to the magnetic force on it too. Is that okay? So if we equate that, then mv squared over r of the charge will be equal to what? Q bvq. Does this make sense? If it's rotated, if we're moving in circular motion, then it means also that it's going to have period, it's going to have frequency, angular velocity, all those things. Do you remember? Okay. So in this case, it means that mv over r will be equal to what? Bq. Do you remember this? V will cancel v. Okay. So that the velocity of the charge is equal to what? bqr over m. Does this make sense? In the case where you are giving all these values. Okay. Another equation that we can get from here is that you know that this guy is also mr of omega squared. Do you remember? So it's equal to bvq. Does this make sense? Or from here, simply say this one is omega. Omega is also what? V squared of v over r. Do you remember that? Okay. So we can say from here that m omega is equal to bq. Does this make sense? Have I screwed things up? No, yeah? Okay, so I can say that omega, angular velocity is going to be what? Omega equals what? bq over m. Does this make sense? Okay, if this is the case, then what do we have? You know that omega is 2 pi f equal to what? bq over m. So what will be the frequency of this guy? bq over what? 2 pi m. Does this make sense? Okay. So what will be the period? Is it clear? Period is always the inverse of frequency, right? So we're done with that. Now the other thing is this. Now, should we quickly talk about, we've talked about it before, right? Motor, right? DC motor. Let me just talk about it in one minute. Somebody say in 1 minute. I won't stay long on it. I just want you to know the direction of motion so that anybody who is watching too. What is this? What are you guys sharing that I'm missing out from? You are. Ooh. So we have north and south. So what is this system called? DC. Somebody say DC motor. DC motor. Motor. DC motor. Now, how does it work? First, what do we use the left hand rule to determine the direction of motion, right? Okay, so magnetic field will be going from north to south in this case, right? Current is going from where? Here to this place. Now let's label the parts. This one is the magnet, right? The stator, right? The one that is not moving, right? Right? Yes, sir. All right, then this one is the armature, right? The armature. Somebody say armature. Then this guy is the carbon brush. This guy is the conductor. Then this guy now is what? Split ring. This guy is what? You see the ring is split. Please don't forget it. DC systems, whether it's generator, or motor uses what? Split ring. But if it's generated, but if it's AC, it will use what? Slip ring. If it's AC, it will use what? Slip ring. So if I wanted to convert this thing to AC motor, what will it become? What will I put? I'll use a slip ring. Does that make sense? Alright, so we want to determine the direction of motion of this thing. Let's just use this left hand rule. So how do we go? Since the direction of electric field is like this, so electric field, magnetic field rather is going from north to south. So we'll put this hand, which is the direction of north to south, right? Then, now, where is current flowing? Current is flowing in this direction, right? In this direction. By the time it enters it to go up here, this side and down here. So on this side, current is flowing up, flowing like this, right? So let this guy go in direction of current. These are current hand, right? So that magnetic field is still like this. So where will this body move? Down. Does that make sense? Invariably, if this guy is moving down, if moving in this direction, magnetic field is like this. Where this side move? Up. So what do you see? Rotation. Do you understand? Good. Everybody. Good. All right. So are we good?
Yes, sir.
So now we are done. We're done. Now let's go to the last part. Are we still going to do simple AC circuit? No. I know, not tomorrow. I'm not doing it again. I've taught you AC now. I will release a video on AC circuit and post the link in the description. Or put the link in the description. Okay, maybe we can just go over formulas alone. Because here, we can't. Time is already far spent. Now, we said the next one is electromagnetic field, right? Electromagnetic induction. Now, who brought about the issue of electromagnetic induction? Faraday, Michael Faraday, right? In 1887. Do you remember? Is it 1886 or 1887? 1887, right? That was the same year. No, Faraday did not live up to. No, Faraday lived up to 1887. Faraday was in 1845. Do you remember? Then this guy was in 1887. Henry Hertz, rather. Hertz. Dear Frank Hertz. Do you understand now? Okay, so we now have an electromagnetic field now. Not just magnetic field. And here we'll be talking about the electromagnetic induction. Is that okay? Electromagnetic induction. Everybody. Electromagnetic induction. What he found out was that if I connect a system like this, a galvanometer, to a solenoid, and I bring a magnet, a permanent magnet, to it like this, close to it, and I bring the permanent magnet like this, then where would this guy deflect? To deflect towards the magnet. Do you get that? To show that current is flowing in which direction? This direction, right? Because it deflects to the direction of current, right? So the moment this north pole comes here, if you induce current here with a south, it's going to move in another direction. Is that okay? So because Faraday wanted to prove the law that the fact that if this thing could create current, if current could create electric field, then it means that if magnetic field could create electric field, no. If electric field could create magnetic field, then magnetic field should be able to create electric field. But he found out that it was the change in magnetic field that create electricity. So he decided to use a magnet, change the magnetic field. Is that okay? So he discovered that the change in magnetic field will induce current on this guy. If you now he saw that when you brought this guy, the magnet close to this guy moved, deflected in the right? If you take it away, it deflects to the left. Is that okay? So it means that as you are shaking it, and the rate of change too matters. Is that okay? All right. If you bring it slowly, it will deflect only a little. If you bring it speedily, take it out speedily to deflect well. Do you understand? All right. So. Somebody say so. All right. He now brought about the law of electromagnetism. So we have the Faraday's law of electromagnetism. Before we talk about his law of electromagnetism, we have to also talk about what is causing that induced current. What causes induced current is actually magnetic flux. And what is magnetic flux? The amount of field lines that are in a group, that are in a band. Is that okay? That is cutting these wires. Is that okay? Or these wires are cutting, either ways. As far as one is changing. Is that okay? If it was the magnet that was stationary and you brought this system close to it like that, the same thing will happen. If it was north, to deflect towards this direction. And I'll show you why it's deflecting towards this direction in a jiffy. Now, the magnetic flux, somebody say magnetic flux. Magnetic flux. magnetic flux is denoted by phi. Is that okay? We discovered that magnetic flux is going to be the strength of the magnetic field over the area that thing is touching, the surface area that thing is touching. Is that okay? In some formulas, you might see cos theta here. Is that okay? Cos theta being the angle between the field line and the angle between the normal to that surface. So if this was the surface that we are trying to induce current in, watch. Somebody say watch. So the normal to this surface here and the angle between the magnetic field line, that will be the theta. Is that okay? The closer to perpendicular it is, the less the area and zero the area. So more magnetic flux will be felt. Is that okay? But because that time this opening will be zero. Is that okay? But the farther from perpendicular it is, the what? The higher the distance. Do you understand now? So the close to zero, the normal to that surface is. All right, so we now have phi we equal to b over d, so that b, our magnetic field strength, can also be what? Phi equals to, no. I made a mistake. The magnetic field is going to be the number of magnetic flux. Do you understand? The magnetic field is going to be number of magnetic flux per surface area. That is number of field lines. How many field lines are touching the surface? Is that okay? So in fact, you can see number here. Is that okay? Number of magnetic field, number of magnetic flux per surface area. Does that make sense? All right. Now, so Faraday's law of my electromagnetic induction now says that the EMF induced, we know that EMF is induced, that's why current is free, right? That the EMF induced is directly proportional to the number of magnetic flux that's per time. Do you understand? Number of magnetic flux that is cutting through the wire per time. Does that make sense? So we know that E will be equal to N this per time. Or we write this way we normally write it. E equal to the change in magnetic flux. And I told you the rate of change matters too, right? dt. We usually add N here to show what? To show that it has to do with number of lines, number of field lines. Is that okay? So that was this mistake here. So that here, phi will now be equal to what? B A cos theta. Does that make sense now? Okay. Now here we can now differentiate. Does that make sense? We can differentiate. So magnetic flux. So this becomes magnetic flux dt because we do want to remove the t. So magnetic flux dt is equal to N d phi. Or either ways you talk about it. Just say if you differentiate this guy, what you're going to have is this. Before we differentiate, let's bring phi. Since phi is this guy, phi is all this guy. Then we have N b a cos theta over dt. So d all of this, right? D everything here. Does that make sense? So if we take the derivative, then E will now be equal to what? N. Now these are constants, right? So they will come out too. D cos theta dt. Does this make sense? Okay. Remember that theta is equal to omega t. Do you remember? So we can say that E equal to what? NBA D. There is something. Before we talk about this, before we derive all this, we're supposed to consider the Lenz's law. Lenz's law says that, I'm going to state it for you again. Lenz's law says that it should be negative minus N d phi dt. What he's saying is that the EMF induced always acts in a direction that opposes the change that what creates it or that produces it. And Lenz's law says that what? That EMF induced is called what? The back EMF, because it always opposes the change that produces it. Is that okay? That's Lenz's law. Okay. So because of that opposition, we'll put a minus. Is that okay? Is that okay? It's a better version of the Faraday's law. So we'll put a minus here, put a minus here, put a minus here, put a minus here. So by the time we take this, d cos theta of what? That becomes d cos omega t dt. So now, So if you want to do cos omega t, if you want to differentiate it, the cos omega t, if you differentiate this, dt, what will this give you? This will be d omega t first, right? D omega t dt dot d cos, let's say u was our omega t. Does that make sense? Dt. So what does this give us? This will give us what? D omega t what? Omega, because t is raised to power 1. Does that make sense? And d cos u what? Sine u. Does that make sense? Are you with me at all? Yes, minus sine u, thank you. So we'll put a minus here. So u is now omega t. You remember u substitution? Okay. So e will now become what? Minus nba minus times minus sine, no, times minus omega sine u, which is what? Omega t. So this minus cancels minus. So e will now become to what? NAB omega sine omega t. So where omega t is 90 degrees, perfectly 90 degrees, what do we have? E will be equal to what? NAB omega. Does that make sense? All right. Is it too much? It's not too much. All right. So we are good. All of us understand the differentiation we did here. Except you don't understand this part. Is it clear? All right, so we have generated that, and that will be it. So quickly, let's talk about what are the use of this thing. We use this induction process. We use it in induction coil, the applications. We use them in induction coil. We also use it in what? In transformers, right? In transformers. And in what? AC generators. Is that okay? AC generators. We also use it in I told you about carbon microphone, but usually you are not tested on carbon microphone. So let's do only these three. Is that okay? Now for induction coil, we are going to talk about induction, right? So now the current that it induces, I said I was going to explain. Should I say explain? The current that is induced, why the galvanometer, the reason why the galvanometer will deflect in this direction, if you bring the north close to it, is this. When you bring the north close to it, Lenz's law says that the EMF induced will go in the direction that will oppose the motion that produces it. Motion is coming like this. EMF will induce. EMF will induce current in which direction? In this direction, so that, wait, if current is induced in this direction, are you with me? What will be the direction of magnetic field? If current was flowing in this direction, current is flowing in this direction now. Where will be the north? Where will be the south? If current is flowing in this direction, which side will be the north? This place will be what? If current is flowing in this direction, this will be where? South. Are you sure? This will be the south. This will be what? You are correct. Why are you forgetting it? You know that magnetic field is going like this. Please master that. Magnetic field is going like this. If you look at it, we said electricity, current is going like this rather. So where will the magnetic field be? If current is going like this, if you look at it here, it's going where? From this side, it's going what? Anti-clockwise, so that will be north. Is that okay? If it's going this direction, at here, if you look at it, it's coming where? No, here like this, right? So if you look at it here, this is what? Clockwise, isn't it? Yes. Is it clear? So here will be south. Is it clear? So if you look at it, there are two magnets. What will happen to them? Repel. Do you understand now? So the EMF induced always produce a current such that it creates a magnetic field that opposes the change that produces it and being more expansive. What it just says is that it creates an EMF that always opposes the change that produces it. Is that okay? Okay. So that's why current will flow. Since current is going like this guy will deflect in the direction of current. Does that make sense now? Okay. Are we clear? Yes, sir. All right. So in induction coil now, we already study induction. So that current that is flowing there is called what? Eddy. Is that okay? I talked about some problem with eddy current. It causes the induction current to heat up quickly, right? And in an eddy current is what causes in inductance. Which one lags behind you? Which one leads in AC? Current leads or current lags? in induction, in inductor coil? Current, voltage. I've told you, listen, L is what we use to represent inductance, right? If you turn L, you use like V, right? So this will be the leader. In capacitance, C, is that okay? C for current too, right? So current leads. This will be the leader in capacitor. Is that okay? I've mentioned this in the former class. You have forgotten now. This guy will be inductor. So in this inductance, in an induction coil, voltage always leads. The voltage always what? So if voltage leads, this is why voltage leads, because of what? Current is what? There's back, there's eddy current. Do you understand now? All right. So, and they lead each other by what? 90 degrees, okay? By quarter of a cycle, that's another thing. Okay? So inductance in a system, if you arrange inductors in parallel too, you know it works like resistor, right? Right? Since it's opposite flow of current in a way too, right? Isn't it? Because of eddy current, right? So it's opposite, so because of that, to work like this guy. So L, total L goes to what? L1 plus L2 plus L3, blah, 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 blah. If you now arrange it in parallel, what will happen? It will become what? 1 over L equals 1 over L1 plus 1 over L2. And energy stored in an inductor is half Li squared. Is that okay? All right. Now, the last part we'll treat, the last calculation is transformers. Now with transformer, we have two types of transformer: the step up and what? Step down. In the step up, see work. We said that this guy has more coil. The input has more coil than the output because it's our load, right? So just check where the load is. That's how you know your output. Now, since the input has more this thing than that, this will be what kind of transformer again? A step down, right? Because we are stepping down what? Voltage. What are we stepping down? Voltage or EMF? Is that okay? That's what we are stepping down. Then, what if the reverse is the case? If the input has less coil than the guy, we are doing what? We are stepping up. Is that okay? So the total power inside the input, in this case, let's call it PI, is going to be what? You know, power is what? Current times voltage, right? That will be I sub S, I sub P if this is primary. Yes, we also use primary and secondary coil. Is that okay? Primary coil is the input coil. Secondary coil is the output coil. So IP times E